One equation tells space to bend, and planets obey instantly. Matter and energy dictate geometry, so shape and motion are linked. That is the basic deal behind gravity in our universe. You can picture space as a fabric, but the math is richer. The fabric stretches, curves, and even ripples when energy moves fast. Curvature redirects paths, like grooves guiding marbles on a board. Light follows those grooves too, because nothing outruns spacetime's rules. Here is the immediate takeaway, spoken plainly and upfront. Where there is energy, space changes shape. Where space changes shape, motion looks like a force. Astronauts feel weightless, yet their paths still curve around Earth. That curve is geometry, not a hidden push. A clock in strong gravity ticks slower, and that affects GPS. Starlight skims the sun, and its path bends by a tiny angle. Black holes are regions where the grooves deepen without end. Gravitational waves are ripples that race out from violent dances. Today we chase the quiet rules, scripting all these dramatic moves. In short, we meet the laws that write geometry. Stand on a hill at night and point a laser skyward. The beam looks straight, but space can make straight mean curved. A geodesic is the straightest possible path through curved spacetime. That path decides how objects move when no forces touch them. This matters for every orbit, every fall, and every satellite ping. Space sets the track, and free objects run along it. They do not choose curves because the track is curved already. Locally, paths look straight because tiny patches look almost flat. Over distance, small deviations add up and the path bows. The metric encodes distances, so geodesics follow its recipe precisely. The Christoffel symbols whisper, and trajectories listen without complaint. Light also follows geodesics, but with a special clockless pace. That is why gravity bends beams and forms Einstein rings. Example in real terms, two small numbers that change everything. Starlight near the sun deflects by about 1.75 arcseconds. GPS signals drift microseconds daily, corrected to keep maps from sliding. Net result, motion in gravity is map reading, not muscle pushing. When mass gathers, clocks slow and rulers squeeze in one direction. Curvature responds to energy, momentum, pressure, and stress, not mass alone. Einstein's field relation ties curvature to that full energy content. You can read it as geometry equals matter, scaled just right. This matters because pressure inside stars deepens gravity beyond intuition. It changes stability, collapse thresholds, and the dance of stellar cores. The Ricci part tracks volume change along families of geodesics. The Einstein tensor packages shape information that keeps energy properly conserved. The stress-energy side lists densities, flows, and internal pressures. Together, spacetime curves exactly as the inventory demands. A neutron star squeezes with ferocious pressure and curves space fiercely. That extra curvature shifts spectra and sculpts pulse timing from magnetars. Gravitational waves carry energy away and leave stretching tracks in detectors. LIGO heard two black holes merge, and spacetime rang in 2015. Bottom line, geometry keeps honest books on every form of energy. Look at the sky and notice its remarkable sameness at scale. That calm uniformity hints at deep symmetries shaping cosmic geometry. A symmetry is a change that leaves the laws looking identical. Such symmetries set constraints, and conservation laws fall out like receipts. This matters because symmetry narrows possible shapes the universe can take. With fewer options, predictions sharpen and measurements speak more clearly. Spatial homogeneity means large regions look statistically like one another. Isotropy means directions look similar, with only tiny jitter remaining. Those ideas motivate a smooth metric for global cosmic expansion. Distances grow with a scale factor, while local physics stays steady. Quantum ripples during inflation got stretched into usable cosmic seeds. Gravity amplified them into galaxies, clusters, and wide silent voids. The microwave sky varies by about 1 part in 100,000. That number encodes the starting roughness that built the cosmic web. Net result, symmetry prunes geometry into a few elegant options. Draw a triangle with laser beams around a galaxy cluster. Add the angles and watch the sum betray the space beneath. Positive curvature pushes the total above 180 degrees. Negative curvature pulls it below while flat lands right on. This matters for fate, lensing strength, and how rulers match clocks. Geometry fixes distances, so it shapes every cosmic yardstick we build. Early sound waves in plasma left a durable standard ruler behind. That scale lives in galaxy separations as faint statistical peaks. Inflation stretched space so much that curvature nearly washed away. The leftover sign is tiny and devilishly hard to catch. Observations compare angular sizes, brightness distances, and clustering wiggles for consistency. Planck maps, supernova catalogs, and galaxy surveys cross-check the scoreboard. Right now, the curvature is consistent with flat to within percent. The triangle test still favors almost zero across independent datasets. What to remember: triangles reveal curvature without touching the material. Follow the gas and you will find hidden scaffolding underneath. Dark matter sets that scaffolding, then gravity pulls everything onto it. Think of a transparent skeleton that only tugs and never shines. It curves space quietly and guides rivers of falling matter. This matters because galaxies need help to grow on schedule. Regular matter collides and heats, while dark matter glides and clumps. Small density bumps grow faster wherever dark matter already collects. The potential wells deepen, and gas streams along filaments to nodes. Shocks light the gas, and stars ignite where flows converge. Mergers stir halos, and black holes feed at crowded centers. In the Sloan maps, filaments span hundreds of millions of light years. Simulations reproduce those strands, with statistics matching observations closely. The bullet cluster shows mass displaced from glowing gas after impact. Lensing maps pinpoint that mass, agreeing eerily with the skeleton. Bottom line, an unseen framework sculpts geometry, and the web reveals it. Rewind the clock, and the universe gets hotter and smoother. Inflation describes a brief burst that blew tiny regions enormous. It is accelerated expansion, driven by almost constant vacuum-like energy. That rapid stretching irons away curvature and dilutes exotic relics. This matters for why everything looks so uniform across the sky. Regions far apart today once shared a tiny, causal patch. A field rolled slowly while its energy held nearly constant. Space expanded almost exponentially, doubling many times in a heartbeat. Quantum jitters in that field froze, then reappeared as classical ripples. Those ripples seeded structure, with a spectrum we can still measure. The microwave background shows a slight tilt in power across scales. Polarization patterns also carry signatures of that rolling field's motion. Observers chase curling polarization that could reveal primordial gravitational waves. A detection would pin the energy scale and test inflation's engine. Net result: inflation explains flatness, uniformity, and those tiny starting bumps. Step back to the present and watch distant galaxies accelerate away. Dark energy is a smooth component that drives this acceleration. It behaves like energy of empty space with negative pressure. That pressure makes gravity repulsive on the very largest scales. This matters for the universe's long future and for yardsticks today. Expansion affects brightness, timing, and how structures stop growing. When the scale factor's second derivative turns positive, acceleration begins. Distances grow faster, while bound systems stay comfortable and local. Supernova measurements in 1998 first revealed the acceleration. Galaxy clustering and lensing later confirmed the same fast expansion. Today's budget is 5% atoms and 25% dark matter. Dark energy takes the rest and sets our ultimate far horizon. Rule of thumb: smooth energy bends geometry gently and everywhere at once. So the picture is, a quiet pressure field steers the universe's destiny. Here is a wild idea shaping how many theorists think today. Space might be built from information, stitched by quantum entanglement itself. The holographic principle says a region's information lives on a boundary. Geometry inside then emerges from patterns encoded on that surrounding edge. This matters because it links gravity, quantum theory, and thermodynamics together. It hints that spacetime is not fundamental, but a woven summary. Certain curved spaces match with quantum systems that have no gravity. Their dictionaries map fields to operators and areas to entropies. Minimal surfaces in the bulk compute entanglement across boundary partitions. Growing entanglement can thicken geometry, like knitting more threads between points. Toy models show wormhole-like connections that track quantum correlations precisely. Black hole evaporation puzzles soften when information accounting stays explicit. Experiments cannot reach these regimes, but consistency checks keep passing. Mathematicians test inequalities, and physicists push solvable corners hard. Bottom line: if information knits space, geometry becomes relationships made visible. All along, one quiet rule kept showing up again and again. Energy shapes geometry, and geometry steers motion, light, and time. That was the deal behind gravity we stated at the start. If this tour sparked ideas, share it with one curious friend. Thank you for watching and keep looking up with patient wonder.